In our last explainer, we talked about the vanishing numbers and the kind of weird world of floating point math. So today, we're going to peel back another layer. We're on the hunt for the ghost in the machine, the clever, almost invisible tricks that hardware engineers use to basically bend the rules of mathematics. All right, let's jump right in.
You know, when you think about numbers on your computer, you probably picture pure, perfect math. But the reality? Oh, it's so much more interesting than that. The numbers whizzing around inside your processor aren't just abstract concepts. They're the result of brilliant engineering compromises, a whole series of hacks designed to make the impossible, well, possible.
And it all kicks off with one massive fundamental problem. How in the world do you represent an infinite spectrum of numbers? I mean, everything from the cosmically huge to the infinitesimally small using a fixed, finite number of switches. In our case, just 32 tiny bits. This is the engineer's ultimate dilemma. With only 32 bits to play with, every single bit is precious real estate. It's a total zero-sum game. If you give more bits to the exponent, which controls how big or small your numbers can be, you have to steal them from the Mantissa, which kills your precision. And if you want more precision, well, you sacrifice range. You just can't have it all. Or can you? This is where the first real piece of genius comes into play. Designers noticed this peculiar little property of binary numbers, a redundant pattern they realized they could exploit to get something for literally nothing. Okay, so check this out. In our normal decimal system, a number in scientific notation could start with any digit from 1 to 9, right? But in binary, it's different. Any non-zero number, once you normalize it, has to start with a 1. It's not a choice, it's just a mathematical fact. And that one simple fact led to this massive, game-changing question. If that leading 1 is always there, if its presence is totally guaranteed, then why on earth are we wasting one of our precious 32 bits to actually store it? It's like writing a plus sign in front of every positive number. It's just redundant information. So what did they do? They just didn't store it at all. This is the implicit leading 1, or as I like to call it, the ghost bit. The hardware simply assumes the 1 is there at the beginning, making it completely invisible in memory. It's the biggest hack of them all. So here's how the trick works. Those 23 bits you have for the Mantissa, they're used to store only the fractional part, all the numbers after the binary point. Then, whenever it's time to actually do some math, the CPU's logic unit just automatically sticks that leading 1 right back on the front, the one that was never actually there to begin with. And here's the payoff, and it is brilliant. By storing only 23 bits but knowing about this invisible 1, we get the effective precision of 24 bits. We've literally gained an entire extra bit of accuracy, doubling our precision, without using any more space. I mean, how cool is that? It's just an absolutely elegant solution. But you know, like in any good story, solving one problem just creates another. This clever system is perfect for all the normal numbers in the middle, but what happens at the extreme edges of reality? What about infinity? Or what happens when we get terrifyingly close to 0? Well, to handle this, the hardware has these 2 secret codes baked in. When all the exponent bits are zeros, or when they're all 1s, it's a special signal to the CPU. It's the hardware's way of saying, hold on, we're off the map now. The usual rules are out the window. So at the top end, when the exponent is 255, all 1s, the hardware can represent things that aren't really numbers. If the Mantissa is 0, you get infinity, like if you try to divide by 0. And if the Mantissa is non-zero, you get nan, which stands for not a number. That's what happens when math just breaks, and it's the absolute worst nightmare for any video game physics engine. But the really juicy problem, the one that's super fascinating, pops up at the other end of the number line. That beautiful ghost bit hack, for all its brilliance, creates a really dangerous side effect as we get closer and closer to absolute 0. I mean, think about it. If the system must always assume a number starts with a 1, then there's a hard limit, right? There's a smallest possible number it can represent. So what happens if a calculation results in a number that's even smaller than that? Well, poof, the system has no way to write it down. The value just falls off a numerical cliff, straight down to 0, and all that data just vanishes. So that's the big question, isn't it? What about all those tiny, tiny values that live in that gap between the smallest normal number and 0? Do they just wink out of existence inside your computer? Well, not quite. To solve this whole cliff edge problem, engineers came up with another, arguably even more clever hack. It's a way to gracefully break their own rules to save the math from completely falling apart. Here's how they pulled it off. When the hardware sees that special exponent code, all zeros, it flips a switch into something called subnormal mode. And the new rule is simple but profound. It basically says, okay team, new plan. That whole ghost bit thing, forget about it. We're not starting with a 1 anymore. We're starting with 0. And this shows the switch perfectly. In normal mode, the value is always 1 point something thanks to that ghost bit. But then, boom, you hit subnormal mode, triggered by that 0 exponent, and the formula becomes 0 point something. That simple change from a 1 to a 0 is everything. It's what allows the system to dive into that dangerous gap and represent numbers far, far smaller than it otherwise could. And what you get is this beautiful thing called gradual underflow. Instead of numbers falling off a catastrophic cliff, they now slide down a gentle ramp towards 0. Sure, they lose precision as they get smaller, but they don't just disappear unexpectedly. And that graceful slide is absolutely crucial for stopping all sorts of scientific and financial algorithms from just crashing. So when you step back and look at the whole picture, you realize your computer isn't just a dumb calculator crunching numbers. It's this dynamic system that's constantly interpreting context, adapting its own rules on the fly, and yeah, sometimes it cheats for the greater good of keeping the math stable. Every solution we've looked at is an elegant compromise. The ghost bit lies about what's being stored to give us free precision. Subnormals break the rules of normalization to stop the whole system from collapsing near 0. These aren't flaws in the system, they're the very definition of great engineering, the art of the intelligent trade-off. And that kind of leaves you wondering, doesn't it? These hardware hacks are completely invisible to us day to day, but they are absolutely fundamental to how our digital world works. What other clever compromises are quietly running everything under the surface, constantly balancing mathematical perfection with messy physical reality? In the next explainer, we'll explore the ULP and subnormal in even more detail. Stay tuned.